Hello everyone, am I audible?
Yes, sir.
Yeah. So it's 7:05 and I think we should start now. So good evening everyone and welcome to the week 10 of the doubt and problem solving session in the course of techniques of material characterization, and we are moving towards the end of this course, and this is week 10, and two more is left, two more are left, like 11 and 12. So I hope that whatever solving whatever problem we are solving, and we are trying to solve as per our module lectures. So I hope that is clear with this sessions, and I hope you guys also that this session is helpful for a better understanding of your lectures as well as solving your assignments. So yeah, so this week we will be seeing some more concepts, and related some problems that will help in your assignment number 10. So before that, I think I have given you one question, and that was very basic. So if you can see, this was the question that I have given you in the last class, that which type of radiation is used in analyzing the crystal structure. So have you guys gone through the lectures, or have you watched the lectures, previous lectures and this week lecture also? So, or do you have any doubt of any lectures? or is it clear to you all till now? So if nobody's saying that, what that does mean? Is it no, nothing is clear or everything is clear? Okay, yeah. So I will imagine that everything is clear. But yeah, so I would like to. So if nobody is answering, or maybe you have forgotten, then I do not know. But okay, let me give you the answer of this question also, which I have asked you before. But since you guys are not giving me explanation, so I will again remaining the explanation part to you guys. And most probably I will be also giving maybe one or two question also, to just think a very simple question, so that that can help to watch the lectures. I mean, if you will not be watching the lectures, then it doesn't mean to solving the assignments, and you can just solve the assignment. That doesn't mean that you will understand all the courses. So for the better understanding, you have to keep making your notes, and it will be always advisable, because whenever you are preparing for the subjects, then your handwritten notes will help you a lot. And I think maybe 2 or 3 lectures back I forgotten that somebody had asked me regarding the reference book, but even I have also forgotten that. So but I will be surely give you the list of the reference book next week. So yeah, for this question, the answer will be the characteristic radiation. And for the explanation, you just watch the module number 9, and there you will all the lectures. I have also given you the hint for this question also. Like I have shown you the interaction volume which you used in the SCM. So okay, let's find. Do not give so much time to the other things. We have problems of this week also. So let's begin. So the first question is the mass absorption coefficient depends on what? Wavelength of X-ray, atomic number of absorber, energy of X-ray, all of these. So if you have watched, can you give me the answer for this question?
All of these.
All of these. Okay, fine. So, hello. Somebody is also saying. Okay, so two students said the all of these. So first of all, the thing is mass absorption coefficient. So, what? What? Was somebody saying something?
All of this.
Okay. Okay, yeah, fine. That is correct. So, can somebody tell me that what is mass absorption coefficient? Your answer is correct. But firstly, before the question that what it is depend on, can you tell me this what is mass absorption coefficient?
Linear absorption coefficient per unit density of the material you consider as the mass absorption coefficient.
What?
Linear absorption coefficient per unit density, rho.
Okay, fine. Yeah, in a one way that is correct. But yeah, okay. So we'll be moving towards this slide. So here you can see that mu by rho. So this mu by rho, what like he has already said, this is the linear absorption coefficient, and this is your density. Okay, so mu by rho is what your mass absorption coefficient. Okay, and here you can see the plot of this mass absorption coefficient mu by rho with respect to the lambda. Okay, so this is your k absorption h. So when you increase the value of lambda, like from 0 and it moving towards a 1.5, and your mass absorption coefficient will also go like this manner, but at certain point, so it will drop, and this is your k absorption age. So you will in the lecture, if you will see that why this k absorption h will occur, then it will it will be helpful for you that to better understand that what exactly is k absorption h and what does it represent and how it will affect the other factors. Okay, but for this question, usually the formula for the mass absorption coefficient is given by k lambda cube into z cube. Okay, so here k is your constant and the lambda is your wavelength and z is your atomic number. Okay, so this is mass absorption coefficient. So mass absorption coefficient is for sure depends on the wavelength, right? And the second is your atomic number. So in the options we have wavelength, we have atomic number, but here mass absorption coefficient decreases since the greater the energy of X-ray quantum, the more easily it passes through an absorber. Okay, so it also depends on the energy of X-ray. So energy of X-ray, so wavelength, atomic number of absorber, and the energy of X-ray. So it depends on the all. So actually here it is saying that the X-ray of wavelength 2.5 angstrom are incident on a sheet of nickel and this wavelength is continuously decreased. Okay, so here you can see yeah, so here the wavelength X-ray is falling or X-ray are incident on a sheet of nickel. Okay, so here it is given by this formula, and at first the mass absorption coefficient for this is 180 centimeter square per gram. So here it is saying from the formula it is clear that it depends on the lambda. So when the lambda is increasing, the mu by rho, which is mass absorption coefficient, will also increase, and z also it depends on the inversely. Sorry, not inversely, proportionally. So mass absorption coefficient, it means the mu by rho decreases since the greater the energy. Okay, so when the energy of the X-ray will be higher, the mass absorption coefficient decreases because it can pass more easily through an absorber. So this is the reason that it will depend on the wavelength, atomic number, and the energy of X-ray. So yeah, all of these is correct. So the moving towards the next question is our material used for the construction of filters in X-ray diffraction are having atomic number 1 less than that of target material with atomic number near 30, having atomic number 1 greater than the target material with atomic number near 30, or the quartz or the beryllium. So what will be the answer?
Answer A.
Okay, so that's mean that the material used for the construction of filters in X-ray diffraction are, it means that which have the atomic number less than or the one less than that of the target material. Any other wanted to give some other answer, or it is the same with you all also?
Same.
Same. Okay, what about others? Okay, so I will assume that it is the same for you also. Okay, so yeah, so here it is saying like you can say you can see that this is the same plot that which I have shown you in the last last problem solving session, and I have shown you that how this why this k alpha and this k beta is coming coming here, and it is superimposing in this plot because you know when you will cross through some threshold voltage, then this kind of k alpha and k beta will come. Okay, so which is known as your vk, if you remember that lecture. So here this is the plot of x-ray and the wavelength. So here the voltage is increasing. So the filter, here it is saying the filter, okay, we use the filter also, and I have also shown you that why what is the need of the filter. That one question we came across in the last lecture, and we wanted to, okay, we wanted to remove some wavelength. Okay, we just wanted to capture only a few certain fixed wavelength of X-ray. Okay, so the filter should be made of a material whose K absorption edge lies between the K alpha and K beta wavelength of the target material. Okay, so this should be, keep in mind that whatever the material you are using, that the K absorption edge. Okay, so this is your, like here in this plot you can see that where the K absorption edge is coming. So it should lies between the K alpha and the K beta wavelength of the target material. So here it is also saying when you will be dealing with in terms of the atomic number, the such material will usually have an atomic number one less than that of the target metal of for metals with Z near 30. So if you are using metal which has the atomic number, usually we use the material which is near z equals to 30. So what we use a material which have atomic number one less than that of the target metal. So this is the reason that uh, okay, so here also so so if you are using a material with Z near the 30, then we have to use a material which have an atomic number one less than that of the target metal. So a filter chosen will absorb. So here what will happen when we will use this kind of a filter, that will absorb your K beta component. Okay, why? Because we want the K alpha. Okay, we don't want the K beta component much more strongly than the K alpha component because of the abrupt change in its absorption coefficient between these two wavelengths, because there will be the changes in the these two wavelengths. So okay, so for an example, there will be the K alpha component, K beta component. So if your filter will absorb the K beta component, because that can absorb the K beta. Okay, it should not absorb the K alpha. Then only you will be able to get the more strongly K alpha component. So that is also one reason of using the filter. So usually the material, just keep in mind that the material which we will be using, that should have an atomic number one less than that of the target material. For the metal with the atomic number which has a Z or the atomic number near the 30. Okay, so yeah, A answer was the right. Okay, so this is also same kind of a question, and I think we have taken this question in the last also, but I have also the same question I think I have came across in this assignment also. So I think it will be very easy for you guys with who has attended the last lecture. So filters are used in XRD to eliminate. I have just told you something about this. Okay, because why we are using a filter. And okay, so let's give the answer for this: K alpha 1, K beta, K alpha 2, or both K alpha 1, K alpha 2. So what will be the answer?
K beta.
K beta. K
Okay,
beta.
okay, so I'm counting three have answered. And what about the others?
Yeah, it's K beta only.
Okay, fine. So most of are given the okay right answer, and which is correct. So that's mean that you guys have uh, gave attention in the last lecture also. So okay, fine. So again, this is the same slide which I will show you that the many so okay, so here also for an example, at this voltage when you are applying a 35 kilovolt, you will be getting this characteristic radiation of K alpha and K beta. But since we don't want a K beta, okay, we only want a K alpha. Okay, so here it is saying the in the X-ray tube operated at a voltage above Vk. Okay, so when you will be going to above Vk, that will not only contain a K alpha line, but also it has a K beta line. okay, in the continuous spectrum. So the intensity of this undesirable component can be decreased relative to the intensity of the K alpha line by placing the filter, because we don't want K beta, we only want this K alpha. Okay, why? Because the X-ray diffraction experiment requires radiation which is closely to the monochromatic as possible. So we don't want any other wavelength of any radiation. Okay, so that's the reason that we wanted to eliminate the K beta radiation. We have to use filter so that we can only get a strongly K alpha radiation or the K alpha component. So that is the reason of using X-ray filter. So yeah, here also you can say it is showing that how the peaks will appear when you will be plotting the X-ray intensity with respect to the wavelength. So here you can see same. So here it is what it is saying, that the partial spectra unfiltered filter of a copper. So here they are telling about when they have used the copper as a target material. So the copper has an atomic number of what, 29, are superimposed on a plot of the mass absorption coefficient of nickel filter. So what just 2-3 slides or in the last question we have seen that the material which has atomic number of near 30, so the filter, so here what they have used, one less than the atomic number. So here what they have used, the nickel which has a one less atomic number as compared to the copper target. So the here it has a Z equals to 29, here the atomic number is one less, it means 28. So when you will see this will be that plot. So it is a zoomed, or you can see a more magnified image of this portion where you will have a K alpha and the K beta component. So this is no filter. Okay, so you will get a K alpha also strongly, but also you will also get some component which is also strongly visible, not as much as K alpha, but yeah, it is visible, but we don't want this. So why, after using filter, see, you can reduce it in a very sufficient manner, and you will be only getting a K alpha radiation. Okay, so this is the reason why we have to use a K filter which can eliminate the K beta. Okay, so here it is also, the thicker the filter, the lower the ratio of intensity of K beta to K alpha in the transmitted beam. So it is giving some relation of intensity and the mass absorption coefficient that can be useful to solve some assignment question if you will have. So yeah, the answer was B, K beta. Yeah, so this is a, since we are dealing this kind of a question since many lectures, I mean when we were starting, when we had our lectures on the Bragg's law, XRD and all, and lambda equals to 2 the sine theta. So Bragg's law is used for what? Just give it very quickly. This is very simple.
D.
X-ray
X-ray
diffraction.
diffraction.
X-ray diffraction.
Great. Okay. I like this enthusiasm. So this is very question, and I will not give so much attention to this slide. So which is correct? Bragg's law. So we all know that the Bragg's law we have seen in our previous lecture is used for the X-ray diffraction. So where n lambda equals to 2d sine theta also. So here in this lectures also you will have to see that the Bragg's law revisited. Okay, and this lecture is very important when you will watch. So here it is also saying that the position of the atom in the unit cell affect the intensities but not the direction of the diffracted beams determined by the Bragg's law. So there will be some arrangement of the atom and in the unit cell, and that will eliminate a reflection completely, saying, and the intensity of a diffracted beam is changed by any change in atomic position, and conversely atomic position can be determined only by observation of diffracted intensities. So yeah, it is again saying about this slide that what they wanted to explain, and I just included this slide also because this is not just the same. This is the Bragg's law revisited, where you will have to where in this lecture you will get to know some new concepts also. Okay, so here like you have seen, this is a powder method of X-ray diffraction. So usually what we usually do is the powder XRD. There are many kind of XRD, like powder XRD, and we do some another XRD also, thin film XRD, and uh, variable temperature XRD. So here the intensity of a powder pattern line depends on the number of one factor which affect the way a crystalline powder diffract X-ray. So it is the same thing. So this is just telling about the powder method or the powder XRD. So yeah, Bragg's law is uh, related to your X-ray diffraction. Quantum theory can account for what? Coherent scattering, incoherent scattering, neither coherent or incoherent, or in other form, if I want to say, is the Thomson and the Crompton scattering, both Thomson and Crompton scattering. Hmm? Somebody give some answer. I could not hear properly.
Quantum theory.
Yes, quantum theory. Have you guys watched or saw the lectures before coming to the session? I think that will be more helpful and the easier for you to, not just to give the answer or to solve the problem. It is not just only what to say, relevant or only till the solving some problem, but it is much more. You can utilize this in a way that it will be good for you to understanding the concepts. So concept is more important. Make a notes, try to remember the things, because when you will make the notes, you can easily revise time to time, and you can brush up your all the old things. Like we have entered into the, like, week 10 has already gone, so I think week 11. So I think your exams will also be coming, I don't know when, but if you will have some short notes, some
The
concepts.
answer is D.
Answer is
D. Both
D.
Thomson and Crompton scattering.
Okay. Okay.
D, answer D.
Answer
D, both.
D. Okay. Fine. So, okay. So, what is Thomson scattering? Can anybody tell me? I just wanted to ask you. Or can anybody tell me what is Crompton? Can you give me any one of these? Or what is Thomson scattering? What is Crompton scattering? Why the quantum theory account for this? Oh, okay. So, have you seen the Crompton effect in the lecture? So, I think it's not just from the my side, but also you have to see the lecture
Yes.
for the.
Crompton effect, when we hit our intensity, whichever coming from the target material, it will hit the electron. It will make the responsible for the oscillation of what slight deviation from its path when you hit it,
Okay.
whichever the electron present in the atom. That will
Okay.
tell you about the Crompton effect.
Okay. Okay. What about others? They also wanted to give, at least I have opened the slides. From this also you can try to explain if you have not seen the lecture.
Whereas, whereas in Thomson effect, when you hit the incident incident beam with the electron, then the electron will oscillate in a certain frequency range. Because
Hmm.
of that, also we are going to generate certain signals. Those signals represent are incoherent with the incident beam. so that that can be mostly effectively we can use it for the that scattering we mostly use for this X-ray diffraction because of the
Okay.
coherency.
Okay. Fine. Fine. Right. Right. Yes. Yes. Okay. So that is fine. So here what he wanted to say or what he tried to explain is that when the X-ray photon strikes a loosely bound electron, okay, so loosely bound electrons means the electron is not very strongly bonded. Okay, the collision will happen which is an elastic one. Okay, so for an example, the X-ray is coming and that will hit your electron which is not very strongly bonded, and that will give you a collision in elastic manner. So the electron, what will happen after this, the electron will get knocked out and the photon is deviated through an angle of 2 theta. Okay, so here you can see this is your electron and this is what your photon. So this is coming, so this will be a before impact. So now it will come and it will hit this electron. So what will happen? The electron is knocked from here. It will come. Electron will knock aside, and this photon, which was in this path, that will deviate through an angle of 2 theta. So this angle from the path will be 2 theta. Okay. So what will happen in this phenomena is that the energy of the incident photon, which was coming this that will give you the kinetic energy. Okay, so when it will hit the electron, so the energy of this photon will be used to provide the kinetic energy so that the electron can move or the deviate. The energy of the photon after impact is less than the energy it's before impact, which is very obvious because now its energy has transmitted to this electron to also knock the side, right? So the wavelength of the scattered radiation is slightly greater than the wavelength of the incident beam. And this is giving some relation. Delta equal lambda 2 by minus lambda. So it is what it is about to say. So this Compton effect was discovered by the A.H. Compton in 1923. And this is mostly trying to say that encounter of the X-ray with the loosely bounded or the free electron. So when it will come and hit your electron, how this will create a path, here your photon will deviate through an angle of 2 theta and your electron will knock aside. So this is your Crompton effect. This is very simple. You just have to read or you just have to see the lectures. Okay, so this is more about the Crompton effect. If you will watch the lectures, you will have a better understanding that why it has developed and what is the more important of this kind of effect or the concepts. So moreover, the question was the quantum theory. So here the answer was the right, but I also have the expectation to answer that what is Crompton and what is Thomson. Okay, so this quantum theory here you can read that account for both coherent, which is Thomson scattering. So the Thomson scattering coherent, and the Crompton scattering, which is nothing but the incoherent scattering, where the wave theory is applicable only to the former. So quantum theories account for both. Okay, so here you can see that the incident photon is coming and this is your target electron at rest. So here what will happen, here your scattered photon will this side and your electron will knock. Okay, so here it will be angle, this is theta and suppose this angle is phi. So the increase in wavelength depends only on the scattering angle. It varies from the 0 to forward direction and it is saying that about this direction and the wavelength, and yeah. So yeah, I hope this Crompton things was clear to you, and this is nothing but this, and this diagram is also saying about this. When the incident photon is coming in the Compton scattering, that will hit your electron and your electron will knock aside and your photon, which is your X-ray photon, will also deviate from an angle, some angle. Okay, So this is your Crompton effect. So the answer was Thomson and the scattering for the quantum theory. So we will also see that what is Thomson, but yeah, somebody has explained that was also correct. So okay, so answer is D. So the relation between atomic scattering factor and the atomic number Z is what? So F is greater than Z, less than Z, equal to Z for in forward direction, or equal to Z in backward direction. So what will be the answer for this question?
So option C. F is equal to Z
Okay,
in forward direction.
okay.
Yes. C answer.
Huh? What?
C, C.
C.
F is equal to Z.
Okay,
C.
C. Others also, please say your answer. Okay, so can anybody tell me that what is atomic scattering factor? Just tell me brief thing or whatever you want. I don't expect that it should be very correct. What you know about the what is this atomic scattering factor?
Generally, it expresses the relation between the wave, whichever the waves that are coming, scattered by individual electrons, uh, which can form the final wave that is coming out of an atom.
Okay, fine. What about others?
That was the main interest here is the electron, whereas for if you go for the unit cell scattering factor, there the interest of incident is the atom. Here we consider as the electron in the atom.
Okay,
That's why if it is there is, because since it is incident, it is scattered with certain angle. That's why it's mostly depend upon the angle and which direction and with which angle that it is interacting with the electron. If it is angle is zero, means it is forward, completely moving the forward direction, means it will equivalent to F is equal to Z.
okay,
It is related with the angle.
yeah. What about others? What do you know about the atomic scattering factor? Now, can you tell me something? I am also giving you the hint. Ha. Okay. So this is usually used to describe the efficiency of scattering of a given atom in a given direction. Okay. So suppose atomic scattering factor. So it is related to the scattering. So what is scattered and what is getting scattered. So this is between, I mean, it is used to describe this efficiency. Okay. So efficiency, the term is in the inverted comma. Just remember. Of what? Scattering of a given atom. Scattering of a given atom. Okay. So there will be the atom which will get scattered and in a given direction. So there will also the direction is also given. So this is represented by the amplitude of the wave scattered by an atom with Z electrons, divided by or by amplitude of the wave scattered by one electron. So this is with the Z electron and one electron. And the other is what? The amplitude of the wave scattered by an atom. So suppose if there is any atom and that will get scattered. So here what will be the amplitude of the wave of that scattered by an atom with respect to the amplitude of the wave scattered by the one atom, which is what? The atomic scattering factor. And when it will be in the forward direction, then it is given the relation of F should be or F will be equal to the Z. Okay, so it is also saying about this will be your 2 theta. So when the theta or when this angle will increase, the wave is scattered by individual electrons become more and more out of the phase and F decreases from F equals to Z. So for the forward direction, the F will be equal to Z. So yeah, that was correct. Now the next is again the same related to the atomic scattering factor, is asking about the relation decreases with the wavelength of incident beam, decreases as diffraction angle increases, remains constant at atomic number when wavelength changes, decreases with increase in X-ray energy. So what is the answer for this question?
Answer B. Decreases as diffraction angle decreases.
Okay. What about others? What they have or in mind with related to this relation? Okay. So why have you think that the decreases as diffraction angle decreases?
No, it's answer D. Sorry, I forgot. Diffraction angle, it doesn't bother about it. Actually, X-ray energy increases means the lambda is decreasing. Lambda is decreasing means sin theta by lambda, whichever you call it, the F will increase. So atomic scattering factor will decrease. Answer will be D.
Yeah. Okay. Fine. Yes. But the answer is A. Now you think.
Oh, show me.
I have given you the answer also. Now you just do your calculation in opposite way.
Yes, you're right. Decreases with wavelength means increasing the sin theta by lambda value, so that F will decrease. Right.
So D was related to the X-ray energy. Here this is related to the diffraction angle. Okay.
Yes,
Just to think
incident
about
beam
the
we need to
sine
take.
theta by lambda. In a halfway you were going in a somewhere right direction, but the later you misoriented. So
Yes,
here,
we need to consider the incident. I just
okay.
round the way
So the
I forgot.
atomic scattering factor depends on the wavelength of the incident beam. Okay. So now you got the answer. The wavelength of the incident beam is okay, but how? How it depends? It is asking whether it is decreasing or whether it is increasing. So what will happen? Um Okay, so this atomic scattering factor will be smaller for when you will use a wavelength of a smaller the shorter wavelength. Okay, so because the part difference will be larger relative to the wavelength when we will be using a short wavelength. So the leading to greater interference between the scattered beams. Okay, so there will be the sine theta by lambda quantity. So when the F decreases as the quantity, sine theta by lambda increases. Okay, so here it is saying, so when the lambda will decrease, okay, so this overall will increase and that will decrease the atomic scattering factor, right? So here the atomic scattering factor will decrease with the wavelength of the incident beam, right? So here with the atomic scattering factor will decrease when you will decrease this value, because when you will decrease this, so this factor will also sin theta by lambda will increase. Okay, when your this factor will decrease, then this whole sin theta by lambda will increase. So here this is showing the atomic scattering factor of copper. Okay, so this is F, which is atomic scattering factor versus the sin theta by lambda. It is saying for the element Z equals to 29, which is copper in a forward scattering, and decreases to very low value of a scattering in the backward direction for a very short wavelength. So when atomic scattering factor decreases with the wavelength, or you can say when the wavelength of the incident beam will decrease. Okay, so here you can see also, here it is also decreasing, and this whole value, the atomic scattering factor is decreasing in this manner. So diffraction is what? Scattering, reinforced incoherent scattering, reinforced coherent scattering. So you have covered till now many diffraction. You have seen what is diffraction, and the principle, and the many things we have seen about the diffraction. Now what is diffraction? And if you have known the reinforced scattering, coherent, not incoherent, so what is that?
Reinforced coherent scattering.
Okay, coherent or incoherent?
Coherent.
Coherent.
Then only
DD.
diffraction will satisfy.
Okay, yeah, yes, yes, yes. So which is right, the diffraction is usually the reinforced coherent scattering, and that is why the diffraction you will get. So which was the right? So here it is saying that this is a full schematic, that the incident beam of a monochromatic X-ray. Okay, and this is your absorbing substance. Okay, so two scattering process will occur. Tightly bound electrons are set into oscillation and radiate X-ray of a same wavelength as that of the incident. Okay, so here there will be, when it will interact, there will be coming out of fluorescent X-rays. Some will cause a heat, some will transmit, and also the electron. Okay, tightly bounded electrons are set into oscillation, and there will be the X-rays, radiated scattered X-ray. So this further, this electron will be Compton recoil electron, or this will be, can be photoelectron, this can be your Auger electron, and this you can use for the for determining the different properties of your specimen. And there will be also, if there will be coming out a scattered X-ray, so whether it could be coherent and the incoherent. Okay, so for the diffraction is usually for from the reinforced coherent scattering. Okay, so the coherently scattered radiation from all the atoms undergoes reinforcement in certain direction and cancellation in other direction. Okay, and that's why this will produce the diffracted beam. And this is also showing that when there will be the electron is not very strongly bounded, then that will scatter part of the incident beam and slightly increase its wavelength in the process, and the exact amount of the increase depending on the scattering angle. So it is giving some relation. But yeah, moreover, it is when the coherent scattered radiation from atom undergoes the reinforcement in some direction, and it will cancel the other direction, which will lead to produce the diffracted beam. So that's why the diffraction is the reinforced coherent scattering. So yeah, that was right. So according to Thomson equation, the intensity of coherent scattering is what? Directly proportional to the square of the mass of the scattering particle, inversely proportional to the square of the mass of the scattering particle, directly proportional to the mass of the scattering particle, or inversely proportional to the mass. So one is the directly or inversely to the square of the mass, directly or inversely to the mass of the scattering particle. So what will be the, if you have seen the formula or the, if you remembered any question, then this question can be helpful to solving the question.
Yeah, boss. We forgot the formula.
Okay. Anybody remember the formula? It's fine. It's sometime happens. Or would like to give the answer.
The answer is B.
Answer is
B.
D. Okay.
Inversely proportional to the square of the mass.
B or D? Are you saying the B or D?
It is B. Square of the mass. Inversely
Okay, fine.
proportional to the square of the mass.
Okay, okay, fine. Huh. So, so here I was talking mainly about this formula. Okay. So this is giving the intensity of a beam scattered by single electron of charge E coulomb, which is in coulombs, and the mass m in the kilogram at a distance r, which is in meters from electron. So here you can see I, and this is m is what mass. So this is the inversely proportional to the square of the mass. So square of the mass of the scattering particle. So here you can see in the formula I equals to I naught mu naught upon 4 pi k square, and e to power 4 divided by m square r square into sine square alpha. So this whole thing become, I mean the mu naught square upon 4 pi, sorry, mu naught square, mu naught upon 4 pi whole square into e to power 4 divided by m square will become your k, because it is constant, where r will be your distance, and this is your angle, and this is your intensity of the incident beam. So you can find out by this formula by putting the value of this all. If your this value will be would be given, that the angle, distance, and the incident intensity, then you can find the intensity of the scattered beam by electron. Okay, so here it is depend on the square of the mass of your scattering particle, right? So this Thomson equation, this is Thomson equation. So it is telling the X-rays are scattered in all directions by an electron. The intensity of the scattered beam depends on the angle of the scattering, and this is the that angle. So this is given this the equation, Thomson equation. Okay, so the answer is B, inversely proportional to the square of the mass of the scattering particle. B. So next is scattering factors are applicable only when the scattered radiation is wavelength much shorter than the absorption edge, larger than or equal to that of the absorption edge, or none of all. None of all.
Yeah, answer.
Okay. What about others? Now can you tell me? So the scattering factor, which is F. So when the scattered radiation has a wavelength much shorter than that of the absorption edge of the scattering atom. Okay, so then only this will happen. So for this scattering, the scattered radiation should have the wavelength much shorter. Okay, much shorter than that of the absorption edge of the scattering atom. So here the answer you will get for this question when you will watch this slide or this lecture. So here it is mainly this is your scattering factor and this will be your sine theta by lambda. So this is for the different element. So this is giving the relation how which I have shown you in the last slide also that I think yeah somewhere here. So this is again the same thing for the different but yeah, so you will get to know that why for the much scattering factors apply when the scattered radiation has a wavelength which will be the shorter than that of the absorption edge of the scattering atom. So for this you have to get to know like where the absorption edge and how it is related to that. Okay, so apart from that, it is again saying about that in Crompton and the Crompton modified scattering and all. This slide is saying many things, but yeah, the answer was A. So an electron into oscillation by X-ray beam. Yeah, this I think somebody has answered, and maybe in the last slide we have discussed. So give the quick answer for this. What will happen when the oscillation of X-ray beam will what? Produce was what? Coherent, incoherent, X-ray electron, Auger electron, what?
B. Produces coherent.
Option B.
Yeah, correct. This we have seen in this, right? So when there will be the oscillation will happen, then the X-ray will come or the radiation of the X-ray of the same wavelength will be coming. So the answer was it will produce a coherent, not incoherent, because the wavelength will be the same coherent X-ray beam. B. This is again related to some filter, which is the characteristics emission are useful for the XRD. So yeah, what we usually eliminate and what you use.
A. We
A,
use
which is
K.
very obvious. We are using for K alpha we are eliminating K beta and all. So yeah, this is very common question K. And oh, I think I have included this again. So yeah, that's all I have collected for this. So do you have guys other questions in mind and would like to interact or
Yeah, I
discuss?
have one question, boss.
Yeah, please go ahead.
Was according to our Thomson effect, okay, because of the oscillations, we are going to generate the coherent scattering, right?
Yes.
That will be equivalent to the intensity of the incident beam, right? Because since it's elastic, it should equal to incident beam intensity only. That's the intensity of that scattered. Huh?
See, the intensity is different because you are talking about the elastic. So it is not talking about the energy. Energy could be, I also have to see, but if it is about the elastic, then the energy
ठीक
can
है भाई, thank
conserve.
you.
But you are how you
सब
can
डिलीट कर
conserve the
दीजिए, एक्सेल
intensity?
मेरा सेव है या नहीं?
Huh?
Sorry.
What?
Was just tell me.
What you have said?
Actually, I'm saying that intensity is equivalent to that intensity of the incident beam. Whichever the intensity of the coherent scattering, will it be equal to intensity of the incident beam since it's a elastic collision, no?
But it is not asking about the energy. It is asking about the intensity. So suppose if your I also have to check, but I think so. Intensity should be difference because it will, incident on some particular substrate or any material. Then it also have some density. Then whatever beam or any is coming input and whatever output will get. So you have to check that with how the intensity should be equal or not. So you just check in the Thomson equation, and I think so. I have given you here also, no? So in some formula, I think so. This no, not this. So yeah, here this is the intensity of the beam scattered, and this is I naught is the intensity of the electron beam. Okay, so I think the I naught will be difference. It should not be equal, even if it is a
Okay, boss. There is
coherent.
one tricky question, boss. According to Thomson equation, the intensity of the coherent scattering is angle of scattering or incident of intensity of incident beam or mass of the scattering particle.
What?
He actually he's saying that according to Thomson equation,
Uh,
the intensity of the coherent scattering, whichever the intensity that is coming right now, according to Thomson, we know that coherent scattering will occur.
yeah.
That intensity is whether it is the angle of scattering or intensity of the incident beam or it is a mass of scattering particle or all of the above. He is not asking if he say which parameter it is depends on, then we can say all of the above.
Hmm.
He is not even using that whether it depend or not. He is saying that what is the intensity of the scattering beam is like that.
Hmm. So here
Are you
it is
getting my
saying na, that X-rays are scattered in all direction by atom. The intensity of the scattered beam depends on angle of scattering. That is Thomson equation. So here all
okay?
will be the constant and only the angle will come into the consideration. So that beam will depend on the angle of scattering.
Okay.
Okay. Yeah.
Thanks, boss.
Yeah.
Good evening, and I have a question for you.
Oh, okay. Yeah. Sure. Go ahead.
It's not about the today's session. I'm asking about the last week assignment question. The
Yeah.
last question, so the 15th question, I think the answer that was given is wrong. The solution manual. I think
What
we
is
have,
that
even though we
question?
have,
15th one?
it was regarding that wavelength and the relation between the wavelength and the voltage.
Okay.
So last class we have solved. We solved using a wavelength of 0.32 nanometer. I think you remember that, right?
Oh, that question
If it,
that we have solved. Yeah.
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 But
Let me
the
just.
issue is that in